So Miniconda has been initialized in my Windows terminal, so I'm just going to open it up and I'm going to activate the Spyder environment where Spyder 6 is installed, and I'm going to launch Spyder. So to the bottom right hand side you've got the IPython console, and you can type in a series of Python commands. So for example, I can type in the integer 1, the integer 2, the float 3.14, and I can type in the string hello. And notice that the return value is shown in the output for each of these. So by default, Python uses single quotations to enclose a string. Notice that hello is white here because the Python interpreter thinks it's object name. If I use the left slash before the quotation, it's incorporated into the string. And for readability, Python has returned this using double quotations to enclose the string. So Python can use single and double quotations to enclose the string. However, single quotations is preferred. And it's recommended to be consistent to the Python interpreter where possible. So we can assign an object name to an object using the assignment operator. So the object is the string hello, and it's being assigned to this object name text. And text can be thought of a label that's just affixed to this object, and the label is used to reference the object. So Spyder has a variable explorer, and we can right click this object text and we can select view with object explorer. So notice that we've got a large number of identifiers, and these are used to essentially carry out some operation on the provided text. So if we type in the object name followed by a dot and then press tab, we see all these identifiers. We can also view the special identifiers. These special identifiers follow the Python data model, so are known as Datamodel identifiers, and begin and end with a double underscore, so are colloquially known as dunder identifiers. So if we type in text dot followed by 2 underscores and then press tab, we will view these. So remember that text is a label to this object, which is the string hello, and if we type this followed by a dot and tab, we view these identifiers. And if we type this followed by a dot, 2 underscores and a tab, we'll view the data model identifiers. So we can also assign the object 1 to the object name whole num. And notice that when we do so, it shows in the variable explorer, and we can view this in the object explorer. So this is a different data type or a different class, and therefore has different identifiers. However, notice when we view the special identifiers, i.e. the data model identifiers, that many of these are consistent. And this is because the integer and the string both follow the Python data model, which is based on the concept of an object. So if we type in whole num dot followed by a tab, we will view these identifiers. And if we type in dot underscore underscore, we will view the data model identifiers. Note that when we type in 1 dot followed by a tab, we don't view these identifiers. And this is because the dot in this case is recognized as part of the number. So this will change it from a whole number to a floating point number. So we can see the difference by using the assignment operator to assign the float to floating num, and we can view this in the object explorer. So notice that we've got a very similar set of identifiers here because these are both numeric data types. However, there are some slight differences because they're not exactly the same. There are some additional tasks that we can do with a whole number that we can't do with a floating point number, and vice versa. So the object name text can be thought of as a label, and when we use this, we retrieve the object. So with assignment, whatever the expression on the right hand side is evaluated, So for example, the expression text will be evaluated and point to the object hello, and this can be assigned to a new label or object name, text2. So now this object effectively has two labels, and we can see that text2 is text, i.e. they're the same object. But we see that text is not whole number. These are two different objects. And if I use delete to delete object name or label, in this case text2, notice that object still exists because it's got the other label text, which can be used to retrieve it. So the delete statement will remove an object name or label, but it won't remove the object itself. When all labels, i.e. all references to an object are removed, then it will be cleared up automatically by Python's garbage collection. So far we have created instances of Python's built-in classes. We can also define our own functions. So here we use the def keyword followed by the function name. We've got open parenthesis for any input arguments, and then we've got a return statement. So this function is going to take no keyword input arguments, and it's going to return nothing. The colon indicates the beginning of a code block, and notice that all the code belonging to the function is indented by 4 spaces. If we type in the function's name, i.e. the object name of the function, we are given in the output that it's a function defined in the main workspace. If we type in the function name followed by open parenthesis, we see that there's no documentation available, and if we input this, then we see that nothing's returned, and this is because the return value was none. So let's now make a function which has a return value, and this function is going to return the string hello. So once again, we can reference this function, or we can call it using open parenthesis. So now we see the return value hello. So now we can add input arguments to our function. So we've got the names of the input arguments, and these are separated by a comma as a delimiter. Notice the space is used to emphasize the delimiter. If we attempt to call this function without input arguments, we get this type error. It's missing the required positional input arguments, input 1 and input 2. And we can also specify these input arguments using their name and assigning them to a value. Notice that there's no spacing around the assignment operator when used within a function call, because we're using the space to emphasize the comma. So the first input argument can be provided positionally, and the second input argument can be provided as a named parameter assigned to a value, also known as a keyword input argument. However, positional input arguments must be provided first, and keyword input arguments are used essentially for optional input arguments normally. So in Python, a function is essentially a block of reusable code. And if we create these two integer instances 1 and 2, if we type in 1 dot and then look at the Datamodel method add, this is essentially a function that's defined in the integer class and can be accessed from all integer instances. So we can call this from the instance 1, which is known as self, and we can apply this to the instance other, which in this case is 2. So if we have a look at the docstring, we see we've got self plus value, which is a shorthand way of writing this. So essentially we can type in 1 plus 2. So this Datamodel function add is defined in the integer class and controls the behavior of the plus operator. When a function is defined as part of an object within its class, it's known as a method. And we can use the plus operator between these two instances using the instance names or we can use it directly between two integer instances. So we can type in 1 plus 2, for example. So now that we know how the plus operator works, we can create a function which is going to take in two numbers and return the summation of the two input values. So if we add the numbers of 1 plus 2, we get 3, and we can use the named parameters here. So now that we've got this function call with the named parameters, notice that within the function call, there's no spaces around the assignment operator because we're emphasizing the delimiter, which is the comma. However, if we assign the value evaluated from this expression to object name or label return value, then this assignment operator is emphasized using spacing. And notice that return value, which is the value 3, is shown on the variable explorer. So if we modify this function, we can set a default value for each input argument. And notice when we don't specify an input argument, the default value is taken. So this is going to be 1 plus 2, which is 3. If we do add nums of 7, the default value 2 is taken. So this is going to be 7 plus 2. If we do add num 7 plus 5, then we've specified both values, and this is 12. If we use the named parameter 5, we're going to take the default value for input 1, which is going to be 1 plus 5, which is 6. And if we only specify the named parameter of input 1, then we're going to take the default value for input 2, and this is going to be 7 plus 2, which is 9. So if we modify this function now to put this slash between input 1 and input 2, and what the slash means is any input argument before the slash must be provided positionally, and any input argument after the slash can be provided positionally or using a named parameter. So now we can specify input 1 positionally and input 2 using a named parameter, but if we attempt to specify input 1 using a named parameter, we get this error. So far, all the code that we've looked at has been line by line in the IPython console. We can save a Python script to documents, and I'm going to call this module 1, and notice it's got the .py file extension. So we can write code in this file. So what I'm going to do is assign the integer instance 1 to the instance name num, and I'm also going to define a function, inches to centimeters, which is going to convert an input argument of inches to centimeters. So notice that I can run this module, and num now displays in a variable explorer and can be accessed in the main namespace, and this inch to centimeter function can also be accessed in the main namespace. So this inch to centimeters function can be used to convert 5 inches into 12.7 centimeters. We can also import module 1. And notice we've got this number 1 in the main namespace. I'm going to reassign this object name to the instance 10. So think of this as the label num, and it's stuck onto 1, and it's just been peeled off 1, and now it's placed onto 10. So that's what reassignment does. So the underlying object isn't changed, but the label has been removed from that object and placed onto another object. So we've got this num in the main namespace, which now points to the instance 10, and then we've got module1.num, which is the value that's defined in the module. And we can also access the function from this module, and we can call it and supply the input argument 10 to convert 10 inches into 25.4 centimeters. So the variable explorer doesn't display modules or functions by default. So I'm going to go to Tools and Preferences and go to Variable Explorer and uncheck this Exclude Callables and Modules. So Open's included in the IPython console by default, but I want to have a look at this module, and we can see that we've got the two objects that were defined, num and inch to centimeters. However, if we have a look at the Datamodel methods, we've got a number of additional ones. So one of these is doc. So this is a text attribute corresponding to the document string. So when we type this in the IPython console, we see the formal representation, and this contains /, which means insert escape character, and then use n, and the escape character n means a new line. So if we print this out instead, what printing essentially does is it processes the escape characters. So this /n will become a new line, and you can see the effect in the printed output below. So we've also got the attribute file, which is another string, and this corresponds to the file path of the string. Now, unfortunately on Windows, the default separator for a folder or file is the /, and we've just seen that this is used to insert an escape character. So what we have in the string is /, and that means insert the escape character /. So when this is printed, you're going to only see the /, which is part of the string that has to be printed. So in addition to the file, we've got the module name, which is also a string. So if I go back to the script editor, I'm working now directly in module 1, so I can access the Datamodel Attributes file and name directly. And what I'm going to do is use the print function to print these out. So we'll see what's printed in the IPython console when this module is run or when this module is imported. Okay, so I'm in the documents folder, which is where this module is. And if I type in import module 1, notice that I've got the printed file path, which has processed the / escape character and shows the full file, and the name of the module is module 1. Notice when I run this that the same file path is shown, however the name is main. And this is because the module has been run directly, and it's classified as the main module when it's run directly by Python. So that's what happens when you use the run button to physically run the module. So quite often in Python code, you'll see this if name is equal to the string main, and this means the module has been executed directly. And if you look at the counter argument, this means the module has been imported. So sometimes there's additional diagnostics code added to a module when it's directly executed, because you're focusing on that module. And that's why there's the differentiation between something being imported and something being executed directly. So we can use the syntax from module import object, or we can specify multiple objects, separating them using the comma as a delimiter. We also have from module import star, and this will import everything from the module. However, it's generally frowned upon using this star for all because it can be quite hard to track what module the items came from, particularly if you're using two modules which both have, for example, num in them. Then if you import everything from module 1 and then everything from module 2, what num are you using? You're going to be using the num from module 2, but you might expect to be using the num from module 1, and this can lead to some mistakes. So let's create another module, module 2. And notice that we can take items from module 1 and import them into module 2. So for example, we can import this function, inch to centimeters, and we can convert 5 inches into centimeters, and then assign this to a return value. So when we run this module, the code in it's going to be executed, and notice that we have inch to centimeters displaying in the variable explorer, and we've got a return value. So far we've examined a simple module, which is a singular Python script file. We can actually create a module that's a folder of Python script files, also known as a package. So let's create this new folder, module 3, and we're going to save a initialization script file to it. So this is _init_.py, and this is the module's initialization file. So if I save this, and now if I import module 3, this will execute the code in the module's initialization file. So the module can also have a submodule. So let's just call this submodule1.py, and notice this is stored in the folder beside the module's initialization file. So we can just add another print statement here. So I'm going to type in exit in IPython console to restart the kernel, and now I'm going to type in import module 3, and this is going to run the print statement. And now I can import module 3.submodule1. And here when we use the dot, think of the dot as referencing an object on the right that belongs to the object on the left. So submodule 1 belongs to module 3 because it's found in the folder module 3. So when we type in module 3.submodule1, think of submodule 1 as belonging to module 3, as it's found in the folder module 3. And then if we type in the dot followed by 2 underscores and a tab, we can view all the Datamodel identifiers that belong to the submodule. And if we have a look at package, we can see that submodule 1 belongs to the package module 3, so that's its root folder essentially. So if we exit, and now what I'm going to do is I'm going to import module 3.submodule1 as an alias, and I'm just going to call this alias submodule. So this submodule can now be used under this alias, and what we can do is have a look at its file and its Package Datamodel Attributes. So here we see the full file path, and the parent folder is module 3, and we can see that the package name is module 3. So within module 3 we can create another folder called submodule 2, and in this we can create another initialization file, and we can just add another print statement to this. So this is another submodule of module 3, and if we save this and exit to restart the IPython kernel, what we can do is import module 3.submodule2. And this is essentially the basic structure for a Python package, and you've also seen how you use the dot to access one object that belongs to another object. And this is a concept that's used in Python's object-oriented programming. So if we go back to module 1, we've got a function here without a docstring, so we can add a docstring by typing in 3 double quotes, and this will give a prompt to create a docstring, which you can select, and there'll be a template for the docstring, and we just need to fill this in. And now in the IPython console, what we can do is we can import this function from module 1. And now when we type inch to centimeters with open parenthesis, notice that we see our docstring. And if we highlight this and press Ctrl and I, we're going to inspect it, and this opens up the documentation in the help pane. If we type in inch to centimeters with open parenthesis in the script editor, we will also see the docstring as a pop-up balloon. So in Python's object-oriented programming, it's quite common to create a module with a certain number of functions that can be moderately complicated and have long documentation strings, and then use these within another module by importing them. So for your convenience, I'm just going to enable the indent guides, and I'm going to just minimize the function. Beginners often confuse a function's return statement with a print statement, and I'm just going to create two functions here which are very similar but use a return statement and a print statement respectively. So in the first function, what we're going to do is we're going to return the string hello world. And in the second function, what we're going to do is print the string hello world. Now this function has no return statement. What this means is it's actually got return none, which is the same as return, and this is the same as not showing the return statement at all. So if we run this module and now compare these two functions, let's just execute the function without assignment to a variable. So here we see we've got the return value hello world shown in output 2. And notice that there's no output 3, instead hello world is just printed, and the quotations surrounding the string are not shown. Now if we assign each function to a return value, notice for the first function that the return value is the string hello world, and nothing is shown in the console because it's been returned to a value. Notice for the second function that the print statement shows because the print statement will always show. And notice that because this effectively uses return none, that the return value was none. So if we have a look at the string hello and then press dot followed by a tab, we see a list of identifiers that belong to this object. So one of these is the method upper, and notice that this returns a new string where every single character in it is uppercase. So this method is a function defined in the string class, and we can call it directly from the string class and then supply it to instance data hello. And when you call a method from the class, it's going to ask for the instance data, and it's going to ask for the instance self to be provided. And when you call the method from the instance data, self is implied. So that's why the parenthesis in the above statement is empty, whereas the instance data needs to be provided in the second statement. And we can also use the Datamodel identifiers. So if we have a look at instance data followed by a dot and 2 underscores, we'll see the Datamodel identifiers, and we can also see these by typing in the string class followed by a dot and 2 underscores. So Python is an object-oriented programming language, and everything in Python is a Python object that follows the Python data model. So there's the objects class, which is the base class of everything. And notice that when you type in object dot followed by 2 underscores, you see the Datamodel identifiers. And you see a similar list of Datamodel identifiers in the other classes, such as the string, the integer, and the float. Many of the identifiers are instance methods. So this means that when they're called from a class, instance data needs to be provided, and this is the input argument self. Notice if we use string.upper without an instance, we have this type error. The unbound method string.upper needs an argument, i.e. self is missing, and we've not provided any instance data for the string method upper to work on. So in other words, it doesn't know what text to make uppercase because we've not provided it an instance with some text data. So if we have a look at the object data model method dir, and we have a look at its docstring with open parenthesis, we see it says default dir implementation. So what this means is that this Datamodel method defines behavior of this inbuilt function dir. So dir means directory, and it essentially treats a Python object as a directory, so as a folder, and every single identifier can be conceptualized as essentially a file within that folder or subfolder within that folder. So if you essentially take an analogy to the modules that we created earlier, the module is a folder with script files or subfolders. So think of the object as being the module, and then all these identifiers that belong to it as being the subfolders or submodules within it. And you use the exact same syntax to access an object on the right that belongs to the object on the left. So to the left of the dot is essentially the parent directory, and to the right of the dot is the specific item that's being accessed. So what we can do is have a look at the directory of the object class and the directory of the string class. So if we compare these left to right, we can see that the string class essentially has all the Datamodel identifiers seen in the object class, and this is because the string is a subclass of the object class and follows the same data model, i.e. the same design pattern as the object class. And if instead of the string class we have a look at the integer class, what we can see is a consistent design pattern, although the integer class has additional data model identifiers that correspond to numeric methods. If we have a look at the directory without any input argument, what we see are the identifiers for the IPython console. I've cleared the IPython console before running this command. So in or underscore IH is the input history, out or underscore OH is the output history, and underscore DH is the directory history. So notice that we've got underscore I, underscore double I, and underscore triple I. This is the last used input, the second last used input, the third last used input. We've also got underscore, double underscore, and triple underscore. So this is the last value that's not been returned to an object name, so it's returned as an output to the IPython console, the second last value and the third last value respectively. So quit and exit both essentially restart the IPython kernel. And what I'm going to do is type in 3 commands. A is assigned to the string 1, the string 2, and the string 3. So notice that in input 1 there's no output because the string 1 is assigned to A. In input 2 and input 3 there is an output. So this means the inputs would be a list, and this would be A equals 1, so this would be a string of the command type here, and then we would have a string of the command 2 and then a string of the command 3. And then you're also going to get underscore I and followed by the number of the input, and each of these will correspond to the string that was used for that specific input. So the input 1 doesn't have an output value. Output 2 has the output, which is the string 2, and output 3 has the output, which is the string 3. So what we have here is a dictionary of key value pairs. So the key is the numeric index of the output, and the value is the value that's returned, which in this case is the string 2 and the string 3. So the directory history is a list of the access directory. So this is just going to be C users Philip documents because we've not changed the directory at all. So from here we can see the third last used input, the second last used input, and the last used input. So the last output that wasn't assigned is this string 3, and we see this in out3. The second last output that wasn't assigned is this string 2, and we can see this was out2. And we don't have any other output that wasn't assigned, so the triple underscore is going to be none at the moment. So we've already seen exit and quit, and we've also got open in the IPython namespace, which is used to open a file. So using dir in the main namespace will display everything the user has created in addition to these IPython variables. What I'm going to do now is I'm going to import built-ins, and I'm going to type in built-ins dot to view a list of identifiers in the built-ins module. So the built-ins module is automatically imported. However, if you type in import built-ins and then built-ins dot, you can see all the identifiers that are automatically available to you when you type in code within a Python script or within the IPython console itself. So essentially at the top are a number of classes in Pascal case corresponding to errors and warnings. We're interested in the lowercase classes, which are the classes most typically used by the user. And these classes are used along with associated functions. So each class follows the Python data model and has a data model method that defines the behavior of the built-in function. So when the built-in function is used on the class, it carries out the code in the class's defined data model method. So this means when you're writing a class itself, you're going to define each of these data model methods, and then when you're going to use the class, you're going to use the built-in functions which these data model methods define. So if we type in builtins.string and we just type in string, these two are the same object. So if we use the is equal to operator, we can see that builtins.string is equal to string, so these are the same object. So within the builtins class, there are a few instances that are capitalized. So this is true, false, and none. So true and false are two instances of the bool class, and these are the only two instances of the bool class. And none is the single instance of the none type class. And the other capitalized identifiers correspond to error classes. So when we examined the directory of the integer class, we've seen that we had a lot more data model identifiers. And these are mentioned in the operator module. So all of these data model identifiers define the behavior of an operator. So before we've seen double underscore add double underscore, which define the behavior of the plus operator. And once again, the data model method will be defined in the class. However, when the class is used, you're going to use the operator. So let's have a look at these object-based data model identifiers. So the data model attribute doc corresponds to the docstring of the class. So instead of using this attribute doc, we typically use the question mark, and we can also highlight the class and press Ctrl and I to inspect it within the help pane. So when the docstring is examined in the IPython output, it's essentially formatted and color-coded, making it easier to read. And a similar type of formatting is done in the help pane. So let's clear the IPython console and create a new module, module 3. And what I'm going to do is instantiate 2 instances of the object class. The object class doesn't require any instance data, so that's why the parentheses are blank. So these display in the variable explorer. And if we type in object instance 1 within IPython console, we see that this is an object at a certain memory allocation. And we can see that both objects are unique because they're stored at different memory allocations. So we can use the string class to instantiate a string. And for the string class, we require the instance data. And we supply this instance data as a string. We can also instantiate a string shorthand using the following. We can also instantiate a bytes string using the bytes class, which is a slightly different text data type. And we can instantiate a bytes instance shorthand using single quotations and the prefix b. There's another related text data type called a byte array, and this gets instantiated typically using a bytes instance. The byte array is typically instantiated using data supplied in the form of an instance of another class and has no shorthand representation. The integer class can be used to instantiate an integer using the supplied integer data. And this can be instantiated shorthand using the integer directly. The Boolean class can be used to instantiate a Boolean instance. And this is typically done directly using the Boolean instance, which you've seen was in the Builtins namespace. And we can use the float class to instantiate an instance of the float class using a provided float. And this can also be instantiated shorthand using the float directly. The above code explicitly instantiates an instance of the class using the class name. However, for built-in classes, it's more common to use the shorthand form. And the class names themselves are generally reserved for casting, i.e. providing the instance of data of a class using another class. So for example, the floating point 3.14 can be cast into a string, and the string 3.14 can be cast into a float. Let's have a look at object instance 1, and let's also print object instance 1. So most objects have a formal and informal string representation. So if we type in object.double_, we can see we've got this repr, and that this defines the behavior of the built-in function repr. And therefore, if we use repr on object instance 1, we're going to see its formal string representation. And if we type in object dot followed by 2 underscores, string __ with open parenthesis, we can see that we also have the string class, which can operate on the object and return the informal string representation. Some classes have no difference between the formal and informal string representation. Others will have a difference when it comes to escape characters. So for example, if we have a look at the instance of the string class, which has the escape character T, which is a tab, and we have a look at its informal and formal string representation, what we can see in the formal string representation is that it's enclosed in another set of quotes. And here we've got left slash, which is an instruction to insert the left slash as an escape character. So in other words, when this is printed, the outside quotations and left slash will be processed. And the string that we will see in the printed output will be exactly how we instantiate that instance of the string class. Let's have a look at the fraction class in the standard module fractions. So if we go to our user profile and then select our Miniconda free or Anaconda free folder, and then go to our environments subfolder and then select our Spyder environment, we can go to the libraries and then we can open this fractions.py. So this is a Python script file. And you can open this up within Spyder, but in this case I'm just going to open it up in Visual Studio Code so I don't change the directory that I'm using within Spyder. So here we see we've got imports at the top, and then we see that we've got the class fraction. Notice that the class has this docstring, and within this class there's essentially a number of functions defined. Notice that most of these functions have self as the first positional input argument, and this means that they're instance methods. So a method is essentially a function that is referenced from an instance and defined in the class. So we can just use fractions. So let's just create this fraction instance 1. And let's have a look at fraction instance 1 in IPython Console. And this is essentially the printing out of the formal representation. And this is identical to what's input to instantiate that particular instance of the fraction class. And this class has a different formal and informal string representation. So let's have a look at creating our own class. So the first thing we're going to do is create a new module, and we're going to save this as coordinate.py. And then we're going to use the keyword class to define the class. So next we give the class name, and we typically use Pascal case. So Pascal case is typically used for classes except for Python's built-in classes, because Pascal case is used to differentiate the error classes from the built-in classes. And recall for built-ins that the built-ins classes themselves are typically used as functions to cast from one class to another. So then we've got open parenthesis, and within the open parenthesis we put the parent classes. So the base class for all classes is an object, which is the default here. And then we use a colon to begin a code block. So within the code block of a class, we essentially define a number of methods. So the static method new is typically not defined and is instead inherited from the object class. This is used to create a new instance of the class. And this new instance of the class is known as self. So the constructor new creates the instance self, and in order to create the instance self, it needs the Datamodel method initialize, which initializes the instance self with instance data. So for a simple 2D coordinate, we're going to need the instance self itself, And then we're going to need the user to provide the X and Y data. And what we're going to do is create this attribute self.x equals X. And recall that self means this instance. And when an instance is assigned to an object name, the object name can essentially be used to reference self. So we're going to have this attribute X and this attribute Y, and we're going to assign the values of these to the values supplied by the user during instantiation. And now I'm also going to create the formal string representation. So what this should do is it should return a string. And the string should essentially be in the format that's used to instantiate the class. So if I prepend the string with F, it's going to create a formatted string, and I can use braces to insert a variable. Now the syntax highlighting in Spyder doesn't highlight the fact that this is a variable, but this is due to be fixed in a newer release of Spyder. So that's the formal string representation. And now we can go for the informal string representation. So the informal string representation will once again return a string. And in this case, we can make the string look more similar to how it does in mathematics. Once again, we can use a formatted string, and we're going to want to insert these attributes. And now I'm going to add the attribute hash and assign it to none. This essentially means that the coordinate is going to be mutable. And I can add an attribute dimension and assign this to 2, just indicating that this is a 2D coordinate. I can also create another custom method that's going to calculate the distance from the instance self to another instance other. So what we're essentially going to do is calculate the distance dx, which is going to be the difference of the coordinates x values. And then we're going to calculate dy, which is going to be the difference of the coordinates y values. And then we're going to square dx and square dy and take the square root to get the distance. And this distance is going to be returned. And now we've defined a basic coordinate class. So we can type in from coordinate, which is the module, import the coordinate class, and then we can instantiate the coordinate. And you see in the docstring that we need an x and a y value, and we can instantiate this to coordinate instance 1, and we can instantiate coordinate instance 2 as well. And we can return coordinate instance 1 to the IPython console. So this is essentially the printed formal representation. We can also print coordinate instance 1, and this is essentially the printed informal string representation. And if we type in coordinate instance 1 followed by a dot and a tab, we'll see all the identifiers that we can call from coordinate instance 1. So for example, we can have a look at its attribute x and its attribute y, and we can have a look at its attribute dimension. Note that the dimension attributes is a class attribute and it's identical for all instances of this class. The attribute y is an instance attribute and it's unique for each instance. We can also use the distance2 method to calculate the distance from another coordinate. If we have a look at the coordinates method resolution order, we see that we've got coordinate and then object. So this means the coordinate class has access to all the data model identifiers defined in the object class. So for example, I can use the inbuilt function dir on this coordinate class, and it's going to take the instructions from the object class and it's going to return a list of strings corresponding to all the identifiers. So in other words, the method resolution order says if the method exists in a coordinate class, use it, and if not, fall back to the defined method in the object class. So the init, repr, string, and hash Datamodel identifiers defined in the coordinate class will be used. And all of the other Datamodel identifiers in the object class can be used because these are defined in the object class and are not modified. So the coordinate class itself should have a docstring. And actually every method in the coordinate class should also have a docstring. These aren't added just to make the code concise so you can see it all together on the single screen. Notice if I import the coordinate class now and highlight it and press Ctrl and I to inspect it, that this docstring displays in the help pane. So a better example is this fraction class, and you can see that every method has a detailed docstring. So let's have a look at the directory of the object class. So some of these identifiers we've already explored. So we know that dir is the directory of identifiers. New is to create a new instance. Init is to initialize the instance with initialization data. We've seen the formal and informal string representation. Let's have a look at class. So what this does is it returns the class type. So this is typically used for an instance to determine what class it is. So this is a string, this is an int, and this is a float. We've had a look at doc, which is the docstring. Let's have a look at equals. And let's have a look at these two object instances. So these are two separate objects and they're not equal to one another. We can also have a look at not equals, which we'll check to see if they're not equal to one another. So we get the Boolean false and true respectively. Now, equals should not be confused with assignment. So notice the difference between the double equals, which is equal to, and the single equals, which is assignment. So if we create object instance 3, which is a second label for object instance 2, and now because object instance 3 and object instance 2 refer to the same object, we can see that they're equal to one another. And we get true when we make the check, and we get false when we make the check for not equal to. So Python has 6 comparison operators. 4 of the comparison operators are used for ordinal objects. The object class is not ordinal, so these are not defined. However, they can be accessed from the object class to see what operator that they correspond to. So we can check these out by using an ordinal class such as an integer. So 1 is not greater than 2, 1 is not greater or equal to 2, 1 is less than 2, 1 is less than or equal to 2. So 1 is not equal to 2 and 1 is not equal to 2. And greater than or equal to is essentially the condition is 1 greater than 2 or is 1 equal to 2. So that's us had a look at the 6 comparison operators. Let's now have a look at the size of. So this is essentially going to return the size of the object in bytes. So typically we don't use this Datamodel Identifier directly. Instead we use the system module and we use this getizeof function. And this returns the memory in bytes. Alright, out of the remaining identifiers, let me just reorganize some of them because some of these identifiers are grouped. So let's have a look at this Datamodel Identifier hash. Now, object has a hash value if it's immutable, as in it cannot be changed or tampered with. And a hash value essentially is a unique number that corresponds to this object. So most of the built-in classes that we've examined are hashable, and this means they're immutable. So once they are instantiated, they cannot be modified. Note that modification and reassignment should not be confused. Reassignment is essentially taking a label off an object and placing it on another object. So it doesn't modify the original object. So notice that most built-in classes that we've examined are hashable. Notice that the byte array instance is unhashable, and this is because it can be modified. So the identifiers append, clear, extend, insert, pop, and remove all modify the instance in place, and these are known as mutable methods. So for example, if I use pop, then the last value of this byte array is going to be popped off. So each letter is represented by a number that's between 0 and 256, ranging over a byte. So essentially the last letter O is popped off, and this has the ordinal value 111. So the Datamodel identifiers get attribute, set attribute, and delete attribute, get, set, and delete an attribute respectively. The first one is immutable, so it does not modify the instance, and the others are mutable, so they modify the instance in place, and therefore only work for mutable data types. So get attribute defines the behavior of the built-ins get attribute, and we need to assign the instance, and then we need to assign the attribute that we want to look up as a string. So this is mainly done when using a loop. So recall when you use the directory function that you get a list of strings. So typically this is used when you're looping through such a data structure to go through all the attributes. So normally you would access an attribute using the dot. So the Datamodel set attribute defines the behavior of the built-in set attribute. So here you're going to need to supply the instance and then the attribute as a string, and then you're going to want to supply the new value. So this won't work for anything in the string class because it's immutable and therefore read-only. So let's import our coordinate class and let's create a coordinate. So C1 is going to be the coordinate of 1, 2. And notice that we've set hash to equal none, so this is mutable. So we can use get attribute on C1, and we can get this attribute x, and it's going to be the value 1. And we can also just type in c1.x to get this attribute. And we can reassign this attribute to the value 2. And if we use get attribute again, we can see that the value is updated. So we can also do this with the built-in set attribute. Or we could use the delete keyword, del, and delete c1.x that way. So as I said, you're normally going to use the dot to access an attribute, and reassignment to set it to a new value if it's mutable, and delete keyword to delete the attribute if it's mutable. So we've seen that the coordinate class is mutable, and this means that it doesn't have a hash value. And you get a type error if you attempt to use the hash function on it. So only immutable values can be used as keys in a mapping. So if you conceptualize a mapping as a set of keys, and you use the keys to retrieve a value. So if you think of a physical key has a lock designed around it, and so the key goes into the lock. Now, if you change the key, it's no longer going to fit in the lock, and that's why only immutable values, i.e. values that cannot be changed, can be used as keys. So a mapping is an immutable object to a value. So in this case, the key is going to be one object instance, and the value is going to be another object instance. And the value is retrieved using the key to index into the mapping. The most commonly used values for keys are strings. So for example, the strings R, G, and B can be used as keys for a mapping that has values corresponding to strings that are red, green, and blue. So the format method is for use within a formatted string. So if we create a space string with a placeholder indicated by braces, we can call the format method from the string, and we can supply this with a variable, and notice that the variable is going to replace the pair of braces in the base string. We can also use a colon to add a format specifier within this base string. So here we're going to specify it's a decimal integer occupying 3 spaces, and we want to display the trailing 0. And the format specifier works as expected. And if we open up the fraction class, we can see the format method, how it's defined here. So the remaining object-based data model identifiers are a bit more complicated and not commonly used by beginners. So if we have a look at reduce x, and get state, we see that these are all helper data model identifiers for Pickle. So Pickle is a Python module that serializes a Python object. So essentially converts an object into a byte string, which can be transmitted, for example, over a serial port. So we can use pickle.dumps to convert an object into a byte string, and pickle.loads to convert that byte string back into an object. And these 3 data model methods essentially help Pickle perform these tasks. So here we've used dump s and load s, which dumps to a byte string and loads to a byte string. And the remaining 2 identifiers are related to subclassing. So this method is called when a class is subclassed and the default implementation does nothing, and it may be overridden to extend subclasses. So it's worth exploring what a subclass is. We've already discussed that the coordinate class is a subclass of the object class. So what we can do is define this init subclass. And this is a class method and not an instance method. So the first input argument is CLS, class, and we're just going to add a print statement here. So we're going to add a print statement here, and then underneath this we're going to use super, and then we're going to call the method from the parent class, which is going to be from the object class. So in other words, we're redefining this class method, but we're saying have the same behavior as the parent class, but add this print statement in it. And now I'm going to make a 3D coordinate class. So I'm going to expand the coordinate class in 3 dimensions. So if I copy and paste this using coordinate as a template, so this is going to be coordinate 3D, and it's going to be based on coordinate. Now, X and Y attributes are already defined in coordinate. So instead of repeating this code, we can call super, which is essentially the initialization method of the parent class, which defines the X and Y attribute. And then the additional behavior is going to be the sed attribute. So then we need to update the formal and informal string representation. And we can also update this distance to calculation. And change the number of dimensions to 3. And we can remove hash because it's going to be inherited from the parent class. Okay, so if I exit to restart the IPython kernel and type in from coordinate import coordinate 3D, I can see that I've made a little mistake. So let me just go ahead and fix this. And you'll see that when I essentially import coordinate 3D, we are using this modified init subclass, so we have this print statement. Okay, so we can instantiate a new coordinate instance that's going to be a 3D coordinate. So notice that we want X, Y, and Z. And now I'm going to have a look at this subclass hook Datamodel method. And this is normally used for an abstract class. An abstract class is used for a design pattern. So the abstract class is not typically used, but multiple other classes will be designed around the design pattern of the abstract class. So let's have a look at an example. So we're importing the abstract base class module, and we're creating this class abstract coordinate based on the abstract base class. So we've got this subclass hook, and it's a class method, and we want to return this all of a list. So all of every condition in the list has to be true. So we've basically got all of these attributes, and the following ones are also callable. Now, because this is abstract class, these methods need to also be defined in the abstract class. And because we're not actually going to use them in the abstract class, we can just use pass in each of the code blocks. And then the attributes at the bottom are non-callable. So we have this design pattern. Abstract coordinate, and then we've got this subclass hook and then coordinate. So we can see that coordinate follows this design pattern, and because coordinate follows this design pattern, we can use the built-ins is subclass to check that coordinate is a subclass of the abstract coordinate, and recall that it's also a subclass of object. So that's me went through all the identifiers of the object class. The last section was a bit advanced, and if you're a beginner and didn't understand everything, don't worry about it. I mentioned it so you would get the concept of the general design pattern, so you can just kind of visualize what's going on when you move from one class to the other, because you see these data model methods over and over again. So we've seen that we can use the question mark to retrieve the docstring of an object, and we can display this in the IPython console or the help pane. We actually also have built-in function help, which can be used to view more detailed information about an object. So if we have a look at the object class, then notice that all these data model identifiers are listed, and below them are the equivalent built-ins. So to recap, new is a static method which creates a new instance. And new calls the instance method in it, which initializes the instance data. And we've got class, which defines the behavior of the built-ins type and is used to return the class type of the instance. We have sys.getsizeof, which is used to retrieve the size of an object in memory in bytes. And remember, we typically use sys.getsizeof. We've got the formal and informal string representations. We've got format for formatted strings. We've got the get attribute, set attribute, and delete attribute. Then we've got the 6 comparison operators. So we've got equals, we've got not equals, and then we've got less than or equal to, we've got greater than or equal to, and we've got greater than. And here in the return you can see the equivalent operator to use. And for something that's immutable, we've got the hash value. So if we have a look at our coordinate function and use help on the coordinate, we see the data model identifiers defined in this class. And recall that a class has a method resolution order. So you're going to first look for the methods in this class, and then you're going to fall back onto the methods defined in the object class. So spacing is quite important in Python, and you should conform to Python Enhanced Proposal 8. I'm going to type in some code that doesn't conform to Python Enhanced Protocol 8. So notice that there's no spaces around the assignment operator, that there's no spacing between the commas within the parentheses, and therefore overall the code is a bit harder to read. So if we go to source, we can format the file or selection with AutoPep8. So notice that this has corrected most of the spacing issues, and the code is now more readable. So AutoPep8 will autocorrect some of the most common mistakes. However, it doesn't correct everything, and that's because there's some slight variations between Python programmers, and AutoPep8 tries to kind of stay neutral between the differences. So as a beginner, it's recommended to read through Python Enhanced Protocol 8, the style guide for Python code. So ideally, you should make your code look as similar to the formatting of Pep8 itself. So there is a note on string quotes, and it says in Python that single and double quotes are both accepted, but you'll notice that the pep8 itself prefers single quotes, and therefore I would recommend being consistent to the pep8 and also built-in Python and the Python interpreter. The other section you should pay particular attention to is the white space in expressions and statements. And if you follow the recommendations in pep8, your code will automatically be a bit more readable, both for you and for other Python developers. So another thing is imports. So what I'm going to do is import the coordinate class from the coordinate module, and then I'm going to create a coordinate, and now I'm going to import the fraction class from the fractions module and create a fraction. So now if I use AutoPep8, notice that the imports are moved to the top. And they're separated into two groups, one of standard modules and another of third-party modules. And in this case, the fractions module is a standard module or standard library, and the coordinate module is a third-party module that we've created ourselves. So Spyder also has an additional code formatter called Black. Black is more advanced in AutoPep8, but unfortunately the developers behind Black have made some design choices which differ to the default representation seen in the IPython Console or official Python documents. One of the design choices is their preference for double quotations. Also, in my testing of formatters, Black seems to only work well after the code has been formatted with AutoPep8. And currently it's a bit cumbersome to swap between the two formatters. However, this is going to be improved in newer versions of Spyder 6. Some of the differences between the two formatters can be seen if I add some more code in. So for example, if I format this with AutoPep8, notice that the spacing around the operators isn't automatically updated. If I manually do this, I might not do it the way that's the most clear. So in this expression, 2 to the power 2 takes precedence. So this can be emphasized with spacing. So notice that the change wasn't made with AutoPep8, but the import for pi from the standard module math was placed to the top of the script file. So if I mess this up and change the formatter back to Black and then format with Black, notice that this expression has changed and 2 to the power 2 is emphasized. At present, Spyder doesn't have the support for import sort, which will automatically sort the imports out alphabetically within the two categories, standard modules and third-party modules. And it doesn't have support for RUF, which is the Rust fast formatter, which essentially brings together AutoPep8, isort, Black, and allows you to create rules for preferences such as single quotations. The RUF formatter is under rapid development and should eventually be brought into Spyder when it's a bit more stable.